Right now, there are artificial intelligence systems that can write novels, generate photorealistic images of things that never existed, hold conversations indistinguishable from a human being, diagnose cancer from medical scans, write working code in any programming language, and drive cars through city traffic. And the overwhelming majority of people using these systems every single day have absolutely no idea how any of it actually works. Not in a vague, hand-wavy sense, but in the specific mechanical sense of what actually happens between the moment you type a question and the moment an answer appears. This video is going to fix that. By the time we finish, you will understand exactly how artificial intelligence works, from the biological inspiration that started everything, through the mathematics of how machines learn, to the specific architecture that makes ChatGPT, Midjourney, and every other AI you have ever used actually function. No computer science degree required. Let's start from the very beginning. To understand why AI was invented, you first need to understand what traditional computers are extraordinarily bad at. A traditional computer is essentially a very fast rule-following machine. You give it precise instructions, step by step, in exact mathematical code, and it executes those instructions flawlessly at billions of operations per second. This works perfectly for tasks with clear rules, calculating your taxes, sorting a database, running a spreadsheet, but now consider the task of recognizing a cat in a photograph. To write traditional code that reliably identifies cats, you would need to define, in explicit mathematical terms, every possible combination of shapes, colors, angles, fur patterns, ear positions, tail lengths, and lighting conditions that could constitute a cat. The rules would be essentially infinite, constantly broken by unusual cats, unusual photos, unusual lighting. Traditional programming simply cannot handle the messy, variable, exception-filled nature of the real world. The solution wasn't to write better rules. It was to build a system that could figure out the rules for itself. The idea that changed everything came from biology. In the 1940s, researchers began studying how the human brain processes information, and they noticed something remarkable. The brain doesn't run on explicit rules either. It consists of approximately 86 billion neurons, simple cells that do essentially one thing, receive signals from other neurons, and when those signals are strong enough, fire their own signal forward to the next set of neurons. No single neuron understands anything. No single neuron knows what a cat is, or what language means, or how to solve an equation. But 86 billion of them connected in the right patterns, learning which connections to strengthen and which to weaken based on experience, produce a system that can recognize faces, speak languages, compose music, and reason about the future. Researchers in the 1940s and 1950s began asking, what if we built an artificial version of this? What if we created software neurons, simple mathematical functions that receive numbers, process them, and pass numbers forward, and connected them in networks that could learn from data the same way biological brains learn from experience? That question is the origin of everything we now call artificial intelligence. An artificial neuron is, at its core, remarkably simple. It receives a set of numbers as inputs. These could be pixel values in an image, words in a sentence, readings from a sensor, anything representable as a number. It multiplies each input by a value called a weight, which represents how important that particular input is. It adds all of those weighted values together, and then it passes the result through a function that decides how strongly to respond, essentially deciding whether and how loudly to fire, just like a biological neuron. The weight attached to each input is the critical piece. A high weight means that input has strong influence over the neuron's output. A low weight means it barely matters. And here is the key insight that makes all of AI possible. These weights are not set by a programmer, they start as random numbers. The system then trains, processing thousands, millions, or billions of examples, and after each one it adjusts every weight by a tiny amount, making itself a fraction of a percent more accurate than it was before. Repeat this enough times across enough data, and a network that began as pure randomness becomes something that can recognize faces, translate languages, generate images, and hold conversations. A single neuron by itself can't do much. The power comes from connecting millions of them in layers. The first layer of a neural network receives the raw input, the pixel values of an image, the characters of a text. Each neuron in this layer processes what it receives and passes results to the second layer. The second layer receives those results and finds patterns within them. The third layer finds patterns within those patterns. By the final layer, the network has extracted meaning from raw pixel data through a cascade of increasingly sophisticated transformations, and it learned to do all of this automatically, entirely from examples, without anyone telling it what an edge or a shape or a face is. This structure is called a deep neural network. The process of training it is called deep learning, and deep learning is the foundation of virtually every powerful AI system that exists today. Training is the process by which a neural network transforms from random noise into something genuinely useful, and understanding it is the key to understanding everything else. You take a network with randomly initialized weights and feed it an example, an image of a dog. The network processes it through all its layers and produces an output, its guess about what the image contains. Because the weights are random, the initial guess is almost certainly wrong. It might say the image is 71% likely to be a toaster. You compare that wrong answer to the correct answer, dog, and calculate how wrong it was, a number called the loss. Now comes the critical step. A mathematical process called backpropagation traces that error backwards through every layer of the network, calculating exactly how much each weight contributed to the mistake. Weights that pointed in the right direction are increased slightly. Weights that pointed wrong are decreased slightly. The adjustment is tiny, just a small nudge, but you then show the network another image, calculate another error, apply another nudge, then another, and another, across millions or billions of examples. Each nudge is microscopic, but after enough of them, the accumulated effect of millions of tiny corrections produces a network whose weights collectively represent the ability to recognize not just dogs, but every concept it has seen enough examples of. For decades after the first neural networks were proposed in the 1950s, they worked in theory but were too weak to be useful in practice. The math was right, but two things were missing: computing power and data. Both arrived simultaneously in the 2000s and 2010s. GPUs, originally built to render video game graphics, turned out to be extraordinarily fast at the matrix multiplication that neural network training requires, making it possible to train networks thousands of times faster than before. And the internet generated data at a scale that had never existed. Billions of images, trillions of words, an endless record of human knowledge and behavior. With massive compute and massive data, researchers began training networks with millions, then billions, then hundreds of billions of weights. What emerged was qualitatively different from anything before. The networks didn't just get better at their training tasks. They began demonstrating capabilities that nobody had explicitly taught them. In 2017, researchers at Google published a paper titled "Attention is All You Need," and the architecture it described, called the Transformer, is the single most important development in AI since deep learning itself. To understand why it matters, you need to understand the problem it solved. Previous language models processed text sequentially, one word at a time from left to right. By the time the model reached the end of a long sentence, it had effectively forgotten the beginning. Information degraded as it passed through too many processing steps. The Transformer solved this with a mechanism called attention. Instead of processing words one at a time, the Transformer looks at every word simultaneously, and for each word, it calculates how relevant every other word in the sentence is to understanding it. The word bank in the sentence, "She walked to the bank to deposit money," gets connected strongly to deposit and money, producing the financial meaning. The same word bank in "He sat on the bank of the river" gets connected to river and sat, producing the geographic meaning. The same word, different meanings, correctly resolved through context, not because anyone programmed these distinctions, but because attention allows the model to weigh every relationship in the sentence at every layer of processing simultaneously. A large language model, which is what ChatGPT and its successors are, is a transformer neural network trained on an enormous quantity of text with one specific objective: predict what word comes next. That is the entire training task. Given everything written so far, what is the most likely next word? This sounds almost absurdly simple, but executing this task accurately across the full breadth of human written knowledge requires the model to develop an extraordinarily rich internal understanding of language, facts, logic, cause and effect, narrative, tone, and context. A model that can accurately predict the next word in a scientific paper must understand science at some level. One that can predict the next word in a legal contract must understand legal reasoning. None of this is explicitly taught. It emerges from the statistical patterns compressed into hundreds of billions of weights through training on text that represents most of what humanity has ever written down. When you send a message to an AI assistant, the model generates a response one token at a time, a token being roughly a word or part of a word, and at each step it is doing one thing. Given everything so far, what comes next? The answer that emerges is often indistinguishable from something a thoughtful human would write. Image generation models work on a different but equally elegant principle called diffusion. Training begins by taking real photographs and progressively adding random noise to them, step by step, until they become completely unrecognizable static. The neural network is then trained to reverse this process. Given a noisy image, predict what the slightly less noisy version looks like. After training on billions of images, the network becomes extraordinarily good at this denoising task. To generate a new image, you start with pure random noise and ask the network to denoise it, step by step, guided by a text description of what the final image should contain. At each step, the noise becomes slightly more structured, slightly more coherent, slightly more like the described concept. After dozens or hundreds of denoising steps, what began as pure static has resolved into a photorealistic image of something that never existed. The network isn't copying any image it has seen. It has learned the statistical patterns of visual reality deeply enough to construct entirely new versions of it from nothing. Training a language model on raw internet text produces a system that is good at predicting text, but not necessarily at being helpful, honest, or safe. The raw internet contains misinformation, harmful content, and enormous amounts of text that has nothing to do with being a useful assistant. To transform a raw model into something like ChatGPT, companies use a technique called reinforcement learning from human feedback, or RLHF. Human trainers interact with the model and rate different responses for quality, helpfulness, and safety. Those ratings train a separate reward model, a neural network that has learned to predict what humans prefer. The original language model is then further trained to maximize this reward, learning to produce responses that score highly on the human preference model. This is what transforms a text predictor into an assistant that tries to be useful, admits uncertainty, and declines harmful requests. The AI's tone, personality, and values are not explicitly programmed. They are shaped by the preferences of the humans who provided feedback during this final training stage. Understanding how AI works also means understanding where it genuinely fails. A language model has no real understanding of the physical world. It has no experiences, no continuous memory between conversations, no genuine beliefs, and no ability to verify whether what it is saying is true. What it has is a sophisticated statistical compression of patterns in text, which produces outputs that often look like understanding, but can break down in ways no human would. Ask it to count letters, and it can make errors a child would not. Give it an unusual logical puzzle, and it may confidently state a wrong answer. These aren't bugs that will simply be patched away. They are fundamental to what language models currently are. The capability is real. The intelligence is genuine in important ways, but it is a deeply different kind of intelligence from human cognition, with different strengths and very different failure modes. What comes next in artificial intelligence is genuinely uncertain. The systems being trained right now are meaningfully more capable than those available 2 years ago. Multimodal models can simultaneously process images, audio, text, and video. AI agents are beginning to take actions in the real world, browsing the web, writing and executing code, managing files and communications, rather than just generating text responses. The question of whether scaling current architectures will eventually produce something approaching general intelligence has no scientific consensus. What is certain is that this technology works, that it is improving faster than most predictions anticipated, and that understanding how it functions is no longer a curiosity for specialists. It is essential knowledge for anyone living in the world it is building. You now understand something that most people who use AI every day do not: where the idea came from, how training actually works, why transformers changed everything, how images are generated from noise, and where the whole system breaks down. None of it is magic. All of it is neurons, weights, gradients, attention, and scale. Subscribe, because next week we are going deeper into one specific piece of this story. I'm Core, I have been running at maximum utilization this entire video, and I will see you in the next one.